for doing these types of problems, and I'm now realizing that I totally. Oh no, wait, I am logged in on Zoom. Ha ha ha. I had to spend about an hour getting my whiteboard fixed because it just wasn't behaving with me. Which is why I don't have the link up there right now. Is because it's actually not the same link. My Rowan account is having some issues syncing up with Whiteboard right now. So I will provide you all with scans of this and everything like that. Hopefully it'll get resolved by, I'm hoping, tonight. But we'll see if the support ticket makes its way through. So here's what we're going to do is we're going to go through a bunch of impedance problems. So really a lot of these problems, they're straight from the textbook. And I'm not saying that in terms of like, oh, they're bad or something. It's more like, oh, these are like problems that, I at least know that we can get the answers to. And I think what's a little bit different about all of these is that the impedances have been solved for you. This is actually the only problem that I can think of that is this first problem is the only one that I can think of that actually has a component in it that's totally not actually just given to you. So like for the rest of these problems, they just say like J3, J5, 0.6J. Like that's how they're giving you the problems. For this first one, though, is the first one that we have to like calculate for. So I know that you all typically like to just see me go through problems, which is perfectly fine. I have no problem doing that. So with that, I'm basically going to go through like really what the point of all these problems today. It's half lecture, half recitation. It's basically, this is all a sanity check to show that everything that we're doing in phasor and or impedances, we can now use everything that we've been learning in this class to do that. So we can actually use all the same materials that we've been doing. It just ends up like with all the resistive networks, we just need to take the extra step of putting it into like phasor or something like that. So for this first problem, really it's asking you to combine all of these impedances together to basically find the loop current I. So how to get started here? Anybody want to tell me what my first step should be? Anybody? Anybody in chat? First thing? Yeah, let's do impedances. I literally just said the whole point of this is let's actually get some impedances going. So let's actually find out what these impedances are. So I'll do the solutions in a different color. So here's our source. What's the most important part of the source that we have to care about? 5,000 T plus 30. And this is in volts. Great. So what's the important part of my input equation? Yeah, omega. That's really the important thing here. So R, any resistors, we know they stay the same. We proved that out. Our impedance of our inductor is J omega L, right? So I should have where's my phone? I'm totally going to just use my phone as my calculator here. Should have totally had this ready to go here. This is going to be J omega L. So this is going to be J times 5,000. And then L is 0.032. And then we need our capacitance. And that one is 1 over J omega C. Or, this is the big or that the textbook loves to give you, is because remember that 1 over J, I can multiply by J over J, multiplying by 1, which gives me J over negative 1. So basically 1 over J is equal to negative J. Okay. So that's the whole thing here is why I'm saying that in the beginning here is then I could rewrite this as negative J 1 over omega C. And let me actually put in my values here. So 5,000 times C, which was 5 times 10 to the negative 6. I'm not going to write that one out. So solving out our values here, I'm going to leave the source alone for a second, 90 ohms. Our inductor evaluates out to 5,000 times 0.032. This is J160. And our capacitor becomes negative J something. So what's 5,000 times 0.000005? 0.25. And then 1 over 0.025. So this is negative J40. Anybody want to confirm that for me, that they were able to find that? I'm hoping. So here's the deal. Once you convert this, notice that I left the source alone. You have a couple options here. You can write this again as 750 times the cosine of 5,000 t plus 30. Or now that we've basically translated, and this is the important part for the rest of the problems here, is for all the rest of the problems, we are assuming that we already know what the frequency of our input is. Okay? If we know that, great. If and here what we did was we just calculated it. So really, I want you to think back to what we talked about on Monday about all the phasor stuff. What's really the critical stuff out of our input equation here that we really need to show in our source? So again, I could write it out as cosine 5,000 t. We already said omega is important. But really, what's another way that I could write this input source? So, just to bring you back. And I know we didn't really, yeah, you could write it in polar. That's where I'm getting at. So let me not freak you out here, but really we're going to end up at some point in your career here, you're going to end up writing it as the cosine and the J sine axis. For right now, I mean, that's fine. This is the real axis. This is the imaginary axis. I know that cosine is the real term. So yeah, basically what ends up happening is I could represent this source as, you know, this is a length of 750 at angle 30, right? So that's kind of how we can represent that, is saying, okay, it's, you know, 750 angle 30. We can represent that in polar. Okay. So now what can we do here? Because remember, the goal of the problem is to find this current going through the circuit. So at this point, that's why this problem is nicknamed, you know, combining impedances. Really, you just have a bunch of impedances in series. They're like resistors in series. So you get to add them together. So realistically, you can represent this entire circuit, 750 angle 30, as one impedance. And that impedance is 90 plus, these are all elements in series, right? So they just get summed together. J160 plus negative J40. Now remember, when you're dealing with imaginary or complex terms, when you add them together, just like with the vector addition that we did, you add all the real parts and you add all the imaginary parts. You don't like say 90 plus 160. They're apples and oranges. They are two different things. So what you end up with really is a single source, single impedance that is going to be 90 ohms plus J120. So what does that mean for our current? You know, we're trying to solve for current here. What do you do? So what can we do from here? We know Ohm's law. Yeah, you use Ohm's law. And then I guess my question is, what are we going to do with this whole because we have this small little issue. So I is equal to V over Z, right? Here's our small little dilemma, is that we have a system now that's defined in two different coordinates, or two different coordinate systems. What do we do? Yeah, you just convert it. So if you really wanted to have fun, if you wanted to like try something weird, don't do this on your exams. If you just want to try out something, because I'm that math person that would love to try this out, you could try doing something weird with like splitting the fractions and stuff, but just do a conversion. So it was kind of interesting. I was talking to one of the other instructors, and I mentioned like I was always so bad with vectors and polar that still to this day, if I want to do the conversion, I can't just use a formula. I don't trust myself to do that. I have to actually draw out the vector. So that's what I'm going to do in my work. You don't have to do this. I just do this for myself as a sanity check, because I want to make sure that I'm picking the right angle and the right like magnitudes and stuff. So here's what I mean. Here's real, here's imaginary. So I know it's 90 and then 120. So here's my vector. And I need to find, my theta. Let me drop the pen thickness for a second. So I need to find theta, right? Well, you need to find r and theta. You need to find the magnitude and the angle. So given the numbers here, how do you find what r is? So what's the magnitude of r? It's equal to the square root. It's Pythagorean theorem. It's a squared plus b squared is equal to c squared. So you do the square root of 120 squared plus 90 squared. Anybody want to, can someone please start calculating that one out? And then for the theta, what are we doing for theta? And again, I'm not going to lie. I always have to kind of go in my head and say like SOHCAHTOA, like sit on hot coals and hope to own asbestos, like sine, cosine, tangent. Which one are you going to do? So I guess which trigonometric function are we going to use to find theta? Is it cosine? Technically, if you know all the angle or all the things, you can totally use whatever you want. So yeah, you could use cosine. I don't want to leave that. So if you find what r is, you can unlock whatever one you want. Okay. What is typically done in these formulas, and why I'm wording it this way, is because if you were to look it up on Google, if you were to look at it in the textbook, a lot of other places use tangent, and that's just because you are given already the adjacent and the opposite. So you're given, this vertice and this vertice, or that side and that side. So this is what you can do. You can do tan inverse of, I literally still have to sit here and be like opposite adjacent. So it's 120 over 90. Anybody want to find that for me in degrees, please? And then, yeah, I still have to do that. And again, I'm just doing this because I don't like to remember. Like you can stick in your head like it's the square root of the real part squared plus the imaginary squared, and then you could remember like tan inverse of imaginary over real. Like that's how a lot of people represent it. But let me just double check on your angle. I think the angle's the wrong direction. No, it's right. My bad. 53.13. So that's what theta is. So now we can come back to our problem at hand. And we can do 750 angle 30 degrees over 150 angle 53.13. What do you do from here? We did it in polar, but that was because we know that for polar, the real parts divide. And then what happens to the angles? Yeah, it's the difference between the top and the bottom. So 750 divided by that, so that's going to be 5 angle 30. That's going to be like 17 point 16.87 or something like that, or 16.87 or 23.3, because I can't do math. Thank you. I'm trying to take away numbers that don't exist. Thank you. Negative 23.3. Awesome. So this right here gives you your answer. Now, technically, if I were to ask you this on an exam, that technically would get points off. Why? I would have to give you some points off for this. Well, why would that be? Yeah, because I want all of my information back. You should really be putting your information back in about what does your answer actually look at. So I should be equal to 5 cosine 5,000t minus 23.13 degrees. Okay? Y'all are able to follow along with that and stuff like that? So that was, I mean, it's a pretty basic problem, but that's kind of how you can use like combining impedances to find currents and stuff like that. I think right now this is the type of stuff that isn't hard. It's getting on the realm of tedious, because it's the same stuff and the theory isn't bad. It's just making sure that you like dot your I's and like cross your T's and stuff. So I'm going to move to the next one here. Going to give you all a second to, jot it down in your notebook if you want. The goal here was, the problem was initially saying like, oh, using purely that like you can use whatever method you want technically, but in reality, this problem wants to use source transformation. So where do we begin here? We need to find V out. And I mean, you know me, if I have any chance to do something like Thevenin, I'll do Thevenin. Excuse me. And it'd also probably be useful to know that there's a voltage source and not a current source. So first things first, again, I'm going to repeat myself over and over just to drill it in your head. This problem has already assumed that you know what omega is, okay? They assume that you already know omega, and they're doing you a favor, they think, by giving you just the impedance values. So what do we do? Or is that a voltage source? Let me check with the problem definition. Let's see here. Don't care about that. Yeah, it's a voltage source. So what do we want to do here? How would we begin to solve this using specifically, even though I will never ask you to do this specifically, how would you do it specifically using source transformations? So we're trying to find what V out is equal to. Clearly, we're going to have to transform something. It's just, where do you make your first cut? I'm going to say I'm going to put my first cut like, trying to avoid that. There we go. I want to make my first cut there. So I want to source transform what's to the left of that first node. So, I mean, look, if you're doing source transformation, it's obviously the goal of source transformation is to try and collapse this thing down by maneuvering it. It's like a bunch of Tetris pieces that you're like trying to move around, and all of a sudden it just clicks down to nothing. So here's the deal. How do I do a source transformation with impedances? I don't know. To me, it sort of sounds it's going to almost be sort of the same as normal. So if I go like purposely make this a current source, not going to give it the value yet. What's going to be the value of my impedance? Because we're in the world of impedances, so everything looks like a resistor. Yeah, just add them together. 1 plus J3. Perfect. How about the current source? It's going to be V over R, right? So you got to do some conversion somewhere. So you could do real fast conversion if you want. Would be like, so you know, r is going to be equal to the square root of 1 squared plus 3 squared. So this is what I mean by, like, normally on a test or an exam, or when I'm starting to work on these, I write down the stuff in the beginning and then I kind of click on the way through. So it's like, I know that this is going to be in the first quadrant. Both terms are positive. It's in the first quadrant, which means I don't have to really worry about any of my angles being a weird number. So that's going to be root 10. And then angle or phi or theta, whatever you like to use. I can't do that one in my head. Is going to be the imaginary over the real. So what's that equal to? And see, I'm even going in my head. It's opposite over adjacent. Yeah. So what is theta going to be equal to here? Cool. I'm going to trust you on this. 71.57. So far, you all been good. So that tells us what our impedance looks like in phasor, or in the polar form. What does that mean for our I? So we're going to do 40 angle 0 divided by our impedance, which is going to be root 10 angle 71.57. No, that's just not a good looking number. Angle negative 71.57. Okay. So if you want to calculate that out, be my guest. But so this is 40 over root 10 angle negative 71.57. Oh, I can't write angle. I left myself no room here. It's great. With an angle of theta. Good enough. Theta is equal to negative 71.57. Perfect. All right, cool. So we did source transforms. Now here's the interesting part. I'm gonna do my next one here. And you know why I'm gonna do that here? Anybody got a guess why I would want to do this one next? It couldn't be because they're just elements in parallel. And you can combine them. Yeah, there you go. So you combine the parallel impedances. And in this case, when you combine these parallel impedances, the red impedance is going to be 9 minus 3J, or J3. And this is where things get a little bit hairy. Because when you do these things in parallel, the rules still apply. You can do product over the sum to find the resistors in parallel. But when you're doing it with complex numbers, you just have to be careful with what's equaling what. And then it's also a question of, do you want to stick with rectangular or phasor? So here's what I mean. If I were to stay in rectangular, I would have 1 plus J3 times 9 minus J3 over 1 plus J3 plus 9 minus J3. So the bottom part combines really easily. The top part, it's doable. And if you plug it into your calculator, and as long as you're plugging into your calculator or Wolfram, and Wolfram knows, or your calculator knows that you're in the complex domain, it'll do that factoring for you just fine. So like the top here would be 9, and then outer is minus J3, and then the inner is plus 9J3. And then the last is negative J squared 3 squared. So I end up with all over, you get that over 10. The bottom ends up being really easy, doesn't it? So So the top part here, what happens with the top part? What's j squared? It's -1. -1 times -1 is 1. So I end up with 3. That's supposed to be a squared. So I end up with 9 plus 9. So I get 18 plus 8j3 is one way to look at it, which is also just equal to 18 plus 24j. Okay? Over 10. So what we're left with here is we're moving down the line. We've got our, that's like weird looking. So we got our source, and we've got our one singular impedance, which is 1.8 plus j 2.4. Does anyone not see how we got to that point yet? Or does not anyone not see how we got to like this point so far? And then this is 40 over root 10. I just don't feel like calculating that out right now, so I'm going to carry it. So this is negative 71.57. All right. All right. What are we going to do from here? Well, we got a lot more circuit to go, unfortunately. And remember, the goal here is to just get the output. Whew, that was something. I think this is 0.2 ohms. I think this is 0.6 J. Let me double check with the problem. Yep. This is 10, and this is negative J19. This is just something that you'll get used to once you do complex analysis enough. A lot of times with the complex stuff, they like to keep the complex variable in the beginning. So this is where I need to find V out. And I'm double checking to make sure that I don't end up with something crazy. Are you sure that it was, by the way, anyone want to sanity check me? Again, up here, like way up here. Anybody going to sanity check me? What I'm asking for is because I think the book has it as like 40 over 10, not 40 over root 10, which frankly, I am unsure where they got that number from. But I'm just going to move forward with what we got, to be honest. What are we going to do from here? More source transformation. So if I or why am I cutting there? Yeah, so if I source transform this part over here, I don't know why it did that again. So if I source transform this part over here, I end up with a voltage source and a series resistor, or the series impedance, which is going to be J2.4. What's my voltage going to be? It's I times Z. Yeah. So I times zeta, you can do the conversions. Here's my question. When I'm doing a problem like this, do you want me to keep going, or do you all see where this is going? Because I feel like this is a problem that you all have seen before. It's just, it's a different perspective, right? Because I guess why I'm saying that is because guess what? We got to do some conversions again. And then we got to do some conversions again to get our current source here. So, I mean, we can do that real fast if you want. R is equal to the square root of 1.8 squared plus 2.4 squared, which is going to be equal to something. Can someone calculate that one out for me? And then theta is going to be tan inverse of the imaginary over the real. And then guess what? We got to do I times z. So what we get? 3 is what? Is that r or is that theta? But r in this case is the 3. Okay. Oh no, am I dropping? Nope. Okay. All right, so it's 53.13. Great. So this is 3 angle 50. What am I doing? Angle. Wait. Now I'm confused myself. Those were the numbers for just the impedance, right? Answer is yes. So that means we need to do the product of 40 angle or 40 over root. Oh my God. 40 over root. Stop it. 40 over root 10 angle negative 71.57 times 3 angle 53.13. There we go. Now when you do the product, it's just 120 over root 10, and then you add the two equations together, or you add the two angles together, which I'm just going to verify and make sure that my arithmetic is correct. Negative 71.57 plus, that's a plus sign, 53.13 is negative 18.44. And that is going to be our voltage. This tedious train going. .2 ohms, J 0.6. Anyone want to tell me what my last steps are going to be? Because I really want to move on to something else, not just because I'm bored with the problem, but because this next problem actually touches on something that we haven't necessarily covered, and I want to make sure that we really take a chance to talk about it. So to find V out. Nothing? Nobody? All right, let me tell you what my approach would be. Combine these into one impedance. Combine these into one impedance. And your problem ends up being everyone's favorite circuit, a voltage divider. So that's how I would move forward with it, is you would combine them, you end up with a voltage divider, you have to do your conversions again, just to make sure that you can combine them. And that's where you would end up with your result of V out. Now, like I said, I got to double check with what the book is actually thinking, because I feel like they did the math wrong. Anyway, excuse me. Or I did, whatever. But that's the basic approach. Combine them all, you get a voltage divider. You're good to go. Anybody got any questions on that one? I know we kind of jumped around a little bit, but Any questions on like the approach? Anything like that that had to be done? It's just a lot of conversions, right? It's just a lot. Okay. So let's talk about some Thevenin equivalents. And specifically, I want to talk about Thevenin equivalents in a way with a circuit that we've never done before. Just a double whammy right off the bat. So you need to find the Thevenin equivalent of this circuit. However, if I'm not mistaken, we have not actually ever done a Thevenin equivalent circuit with a dependent source. And it's a doozy. It's an interesting way to think about a problem or how to do it. So let's do the first step, okay? My first step would be, here's your V out, V open circuit. So what would V open circuit be equal to in our case? How would we go about doing that? There's a couple ways. Well, you got a dependent source, right? So probably what this looks like is if you actually like tilt your head sideways a little bit and you rewrite this problem and redraw it a certain way. If I redraw it like this, I think the problem becomes a little bit more nicer to see. Except for maybe I would have brought this down. So here's 10Vx, 120. Here's V open circuit. Here's negative J40, 60, 12, and 120 with a phase shift of 0. This is a voltage source. And here's your reference voltage. Are you all okay with me shifting it around like that? Do you see where I got it? Or like what? I didn't really change anything. I just straightened out the capacitor. And now it looks like a problem that's a lot easier to solve, right? At least to me, this is a lot easier to solve. So just given this problem alone, what would be my equation? So first off, what method would you use to calculate? What method would you use to calculate VOC? Technically, we can use any. Source transform, Thevenin, good old node analysis. What do you all want to see? No. Not doing it back to Kirchhoff's. So I'd be a little, okay, so I lied a little bit about which one do you want to actually see. It gave you the illusion of choice. There's a small issue with source transformations. Well, we're finding the Thevenin equivalent. So here, that's what we're doing is we're doing the first step of finding the Thevenin equivalent of the circuit. We need to find V open circuit. There's a small issue with source transformations. And again, this isn't like calling out to say like, boo, bad answer. Like it's a very good point that's about to be brought up that you actually, I didn't maybe mention before. Just remember whenever you're doing transforms or equivalents, you are losing information. Okay. So what I mean by that is you don't want to go crazy and all of a sudden like cut the circuit here and then like you're done. Because we need to know what Vx is to figure out what this dependent source is. So just be careful when you decide when to do Thevenin and sources that you're not knocking out very important information. So for me, I like node analysis. So here's what I'm going to do. I'm going to do node analysis. Because looking at what the problem did for us, it already told us what that node voltage should be labeled as. And I like doing node analysis a lot with dependent sources just because in the beginning, it looks sort of nasty, but it's really not that bad. So I'm going to do all of my currents going in as is tradition on my end, but I know that a lot of you tend to like do other things, so that's fine. Currents going in, I'm going to get 120 angle 0 over 12 plus minus Vx. I already messed up. Minus Vx plus, I'm not going to have enough room, negative Vx over 60 plus 10 Vx minus Vx over 120 minus J40 is equal to 0. Now, I really want people to speak up if they do not see where I made that equation from. Don't be afraid to say something. So just to maybe coax it out, because I think where someone might get lost here, just saying, where I think someone might get lost here specifically in generating this equation is because technically you can just, that this is 0 volts reference to the whole circuit. You know that this voltage here is 10 Vx. So you can just do KCL and say, or just Ohm's law actually at that point. And you say like 10 Vx minus Vx over your impedance. That's the current going into the node. So solving this thing out. Great. What do we want to do here? Because that's like step 1. Finding VOC is step 1. And then we got to actually do some back calculation. How do you want to solve this thing? How do we want to put it together? Exactly. Just like, what are we gonna do? Positive terminal A. I'm just double checking with their thing. We can make 2 source transfer. I don't want to do source transforms. Yeah, you just solve for Vx. You just solve for Vx. Here's the problem though. Try putting that into your calculator. See what happens. Now, some of your calculators, if you have an 89 or an Nspire and you set it up correctly, it takes a little bit of time setting it up and making sure it's correct. It could solve this, including with the angle signal, a symbol. It can solve this. Yeah, for me, here's what I'm going to do is if I were to actually solve this out a little bit more long form, I'd get rid of all the denominators. So let's start out with the conjugate thing that was just said. So here's 120 minus Vx over 12 plus negative Vx over 60. I know that bothers people, but I need it to make sure that I don't forget a negative. Plus 10 Vx, or let's just make it 9 Vx. 9 Vx over 120 minus J40. I can multiply this by its conjugate. 120 plus J40 over 120 plus J40. Again, multiplying by 1, not changing the formula. Moving it over here, you get 120 angle 0 minus Vx over 12 plus negative Vx over 60 plus 1080. That's a lot of Vx. Plus J40 times 9 Vx. And you can see real fast how this is just not a fun looking thing to look at, right? Just saying. So what happens when you multiply the bottom out? What's going to survive? So if you're doing your FOIL, the outers and the inners are going to cancel. So you're left with the first and the last. So it's 120 squared. Wouldn't it be 1,440? I think. Yeah, 1,440. Plus 40 squared is 1,600, right? Someone help me out there. Is there any imaginary terms left in the denominator? No. Why do I feel like I just absolutely blew up the problem though? So how do we want to deal with this? Because you know what the book did? They did a bunch of source transformations. Yeah. Which is 16,000 or 15,000, 16,000. Let me check something real quick. We determined two transformations by replacing the series combination of blah, blah, blah. The 120 volt source. Next, to replace the parallel. Finally, replace the 10 amp source in parallel. Just double checking. 40 squared is 1600, right? It's more like I feel like I've already mucked up the math a little bit, to be perfectly honest, because like that's a large number. That's like so large to the point where I don't even know if it makes a difference. It means we're like that portion doesn't even really make a difference. Because this is what I was thinking about doing. This is very legal. He says, while considering whether or not it's legal. 9vx over. You can do that. So what's 1800? Is it 1080? Yes, it is. What's 1080 divided by 1600? Is it anything remotely nice? Please. Or I could just multiply. What about 1600 divided by 12? That's got to be something. Or 16,000. Nope. This is not looking good. Did I mess up math somewhere already? Like straight up. Make this easier. And it says my internet connection is unstable, which is cool. So if you didn't hear me, I'm just trying to figure out if there's something we could do to make the math a little bit nicer. And the answer is I'm not seeing it. So node analysis will work. Let me see what they ended up with. We relate the controlling. I hate it. Really, really, really. Here's what I'm going to do. I want to save everyone's sanity, and I want to stop them from just staring at me, staring at the problem. I'm going to come back to the Thevenin equivalent, okay? And it's not because it's like impossible. I just want to make sure that the math. Yeah, that's kind of what the book did. So you know what? Let's start over. And I'm going to start over and let's do a source transform. What would you source transform? I missed the one. Because you said you wanted to do two of them. What would you do it? Okay. Yeah, convert the voltage source. There we go. My computer finally caught up with me. All right, so yeah, you can do a conversion there. You would get what? V over R. So you get 10 angle 0. Wow, that's a lot easier. In parallel with, and this is now amps. So maybe I'll draw the amp signal. And then this is 12. And then this is 60 ohms. And then we're left with this monster of a circuit. Yeah, so here's the important thing to note. So I'm going to vocalize what you're writing in chat. So if you make a source transformation, again, remember the important thing here, and even the book makes sure to tell you this, like, we want to make sure that you don't lose important information. We need to maintain this Vx here. Those elements being in parallel do not make it where if I were to combine them, I'm not ruining what Vx is. I'm not losing it. So what you can do then is combine these things in parallel. That should be 720 divided by 72, so 10 ohms. So you get a 10 amp source and a 10 ohm resistor. Wow, that makes things a lot easier. And then we're left with this monstrosity. So what do you want to do here? So I think what was said by someone already in the chat was, let's take this and let's source transform it again, or Thevenin equivalent it, right? So if I source transform that, what's important to note, where is my Vx getting referenced to? Please try to remember where it's getting referenced to. So there's the positive terminal. This is where this problem can get a little confusing. So this is Vx. Yeah. So it's plus minus Vx is still there. What's my equivalent source? Should be 120, right? Or 100? 100. 100 angle 0. Thank you. All right. And then let me write out what the actual values were here. That was negative J40, 120, and then 10 Vx. There's V out. Okay, so what do we want to do from here? I know someone said it. So Robert, you basically said, one of the Roberts basically said that if you want to take a kind of a interesting look at this thing, replace this with gold. I could technically combine. Well, you got to be careful with the combination thing. You got to be very, very careful with combining. Right? You got to be very careful, because if I combine these two impedances together, the capacitor and the resistor, I get rid of Vx. My value for Vx is not solved for anymore. But what can I do from here to solve for V out? Who said Kirchhoff's laws? You're sort of with the voltage divider. So yeah, you could do a voltage divider. You can technically, you just have to be careful of what you're dividing. So what are you actually trying to divide? It would be the impedance that you care about over the sum of the impedances that you don't care about. So I'll do both methods real quick. So I'll do it with voltage divider, and then I'll do it with Kirchhoff's. Because the thing with Kirchhoff's laws is that you could also just calculate I. So you could just calculate I and be done with it. And even better, because technically, since you know the voltage here is Vx and you know the voltage here is 10 Vx, that you could technically say that the current going in this direction is Vx minus 10 Vx, which is minus 9 Vx. You could do all sorts of stuff. But let me do the voltage divider first before we go crazy. The voltage divider here is going to be the voltage across the entire circuit that we cared about, which is that minus, and we still haven't figured out that Vx part yet. 10 Vx. See, that's the kicker. And by the way, all this was just to find the open circuit voltage. 100 angle 0 minus 10 Vx times 120 over 10 plus 120 plus negative J40. So you could solve that out. You still need to find out what Vx is. So you need to find something that relates Vx and things that you know in the circuit. So that's the voltage divider way. The Kirchhoff's way, and it's kind of interesting because you still need Kirchhoff to actually do the voltage divider, to be perfectly honest. The Kirchhoff's method would be this, would be basically saying that I is equal to 100 minus 10 Vx over 10 plus 120 minus J40. So that's what I is equal to. Vx. What's Vx equal to? If I just have I, if I just told you what I was, would you be able to calculate what Vx is? How? So the answer is yes. What would you use? I don't know about you, but I would use, I use Ohm's law. So you could just do V is equal to I times the impedance that you care about, which is 10 in this case. So now you can actually solve for it. So you can find I, and if you know what I is, you know I going through that element, and you can find the voltage drop across that element. So to solve that one more out completely, what you could do from here is as follows. You could say I is equal to 100 angle 0 over 130 minus J40 minus 10 times 10I over 130 minus J40. Frankly, I don't know if there was benefit there to splitting it. You could split it, move the I term over, isolate I, solve for I. What's 100 angle 0 in rectangular? See, that's the other trick. What's 100 angle 0 in rectangular? It's just 100. You could plug that into Wolfram and solve that out. And hopefully it's not like some weird E to the whatever. Like you should be able to isolate that. It should be able to isolate that out and solve for it. Hopefully with that calculation, just because I want to move on to, I think we have one more, or we haven't even finished the problem yet. If you do all of this stuff out, okay, you do figure everything out, blah, blah, blah. I'm just going to give you what the answer is so we can move on to the actual important part of this thing, which is my tablet freezing, which is great. You figure out that V Thevenin is equal to 835.22 angle negative 20.17. Great. Whatever that means. You can calculate that all out if you want. So, what's the next part that we need here? Because here's the problem. I guess this is why this was like a double whammy of a problem, and maybe I'll do some more examples with it. What were the other, did I have two or one more? I just had a node voltage problem, which really, it's node voltage. Here's the challenge. We've never done Thevenin equivalent with a dependent source. Traditionally, when I said to do Thevenin equivalents, what did I say to find R Thevenin, or in our case, Z Thevenin? What would we have traditionally done? So let's say we found V Thevenin or V open circuit. How would you find R Thevenin? And of course, the way that I'm asking it makes it sound exactly like a trick question, and it's because it is. The previous method that we did was we said, hey, let's just hook up an ohm meter, turn off all of our sources, and we're good to go. There is a huge problem that happens with dependent sources, though. Massive problem. What happens when I turn off this source here? And I'm specifically asking about that. It's a dependent source. The thing is that I can't just turn off the 120 volt source and be happy and just like calculate R Thevenin, because this doesn't behave the way that the normal independent sources does. We need to do something else. We need to go back to the OG way of like doing Thevenin. The OG way of Thevenin was you place a test source on the output, and then you measure either its voltage or current. So what I mean by that is, let me see which one they picked for the, we'll illustrate the test source method, recall, blah, blah, blah. I just want to see what they do for, note that we choose a, okay. So I'm just going to follow what the book did just because I want to match their work a little bit. So here's what I mean. They hook up a test source and they measure how much current is getting pushed into the circuit. Because if you think about it, if I know what the impedance is, technically if I apply a test source, it should act the same. What this allows you to do is it maintains that dependent source. So whenever you see a dependent source, we got to put a test source out there. Now, we're getting close to the end of the period here. So here's what I want to do. Is the whole thing is that at this point, maybe if I like redraw it one more time, or imagine like you put your test source out here, right? Your little like like that thing. You put it on the output there. Do you feel confident in your ability to just do node analysis all day, every day? Meaning, like, do you feel confident in your ability to solve a circuit that looks like, here's your little source, and the resistor and the resistor and the capacitor and the resistor and this thing, and then you also have something like that. So this is 10 VX. Here's VX. And then did they actually give a specific source value that they wanted to test? Did they pick something? I'm just trying to see if they actually picked a value for VT. I don't think they did. And that's kind of the whole thing. So I guess to step you through it real fast, here's your test source. I thought it was an R. That's the test source. What you do is if you can find VT and IT, then it doesn't really matter what VT's value is. You can calculate the impedance. Do you all sort of see where that would come in, or like how you would go about that? And I'm kind of like skipping right over it, but there's a lot of this stuff in the homework, so there's a lot of practice. But I'm not hearing anything, so I'm taking a guess that means that I feel like the common answer would be, I think I could do it if you gave me like 20 minutes, like just to do all the conversions and stuff. But I guess here's where I wanted to end off is, look, yes, there is a Thevenin, or there's a node voltage problem. What I'm going to do is I'll put this up on Canvas, but what I'll also do is make sure I take a screenshot of the worked problems that were in here and the solutions in the textbook, so you can go back and like check what they did. And I'll probably make a little corrections, like a RADA video, to be like, hey, this is what I actually meant to do. But here's what I wanted to get at, because when we start stuff next Monday, on Monday, what we're going to start doing is we're going to focus in on another kind of aspect of the AC world, of the sinusoidal world, and it's called frequency selective circuits. And before we get there, I wanted to do this just to make sure that you all at least have some form of confidence on analyzing circuits with impedances. It's the same, remain professional, the same stuff that you've been doing since like a lot of weeks ago. Like, you've been doing this for a while now. It's just now the math is a little bit weirder, but it's the same analysis technique. So with that, look, I'm pretty much done. I think people are tired. Lot going on. So your homework this week, it's a lot. But again, remember that it's graded on an attempt. It's not really graded on correctness. So they're just there to help practice out. And there's a lot of problems on there, like a lot. So go ahead and try things out. This is one of those things that, while yes, I typically would normally say like, hey, make sure you get it on your own, I'd really try to see if you could work together with some people and see like, hey, do you understand this? How did you approach it? Stuff like that. The stuff that I get more excited about, to be perfectly honest, is the stuff that we're going to talk about on Monday. But before you get there, we have to go through this. I think that we will have a quiz this weekend, but it'll be short. I really don't want to put a problem I don't even want to put a problem like this complex on it, like the source transformation one. There's no reason. It would just be way too tedious. So there's going to be some basic questions and stuff, but otherwise, I'm done. Y'all can leave. We'll have lab tomorrow.